Good afternoon, everyone. Thank you all for coming. I'm delighted to be part of this wonderful celebration of the birth centenary of one of the important professors who taught at AC Tech, Professor K. Chandrasekharan. I'm very grateful to Dr. Sukumar Devota and his colleagues at AC Tech who have taken the effort to organize this birth centenary celebration, because it is absolutely important that we all remember our teachers and celebrate their life for the gift they bestowed upon us. The gift of knowledge is invaluable. And in some cases, it can change someone's life quite dramatically. And in fact, that's what happened to me when I was an undergraduate student at AC Tech some 50 years ago, which I'll mention as the talk develops. So it is absolutely important that we organize such celebrations. And I would like to thank Dr. Devota also for kindly inviting me to share my work with you all on this wonderful occasion. I wish I could be there in person. I'm unable to do that because of my teaching and other commitments here at Columbia University in New York. And as I mentioned, I wish I could be there in person, particularly because the Raman Auditorium, where this lecture is being delivered, is a special place to me. Although I've given hundreds of lectures all over the world, Raman Auditorium is very special to me because that's where I gave my very first talk as a fifth-year undergraduate student in chemical engineering at AC Tech in September 1976. So that's where I gave my first lecture, and so Raman Auditorium has always been a special place for me. And so as I mentioned, it is important to celebrate our teachers, and I'm going to begin by recalling some of the wonderful teachers I've had, many at AC Tech, but one particular one, before I arrived at AC Tech, I was a student at Central Polytechnic in 1971-72, where my physics professor was Professor K.C. Dorairaj, shown here. He was an unusual man. He didn't have a PhD. I suspect he didn't even have a master's degree, but he had an amazing sense of kindling someone's curiosity in research. And so it is because of his lectures on physics more than 50 years ago, 52 years ago now, that I fell in love with physics and also with research. And I developed this intense desire and curiosity to understand everything deeply in terms of fundamental principles. And I would point to Professor Dorairaj as the person who kindled that flame of intense curiosity in me. And that was followed by my arrival at AC Tech in 1972. And for the first 2-3 years in the physics courses, Professor P.R. Subramaniam was the physics professor for some of us. There were 2 sections. I was in the second section. And PRS, as we called him affectionately, was a wonderful man. He's an amazing teacher. He was also doing his PhD at the same time with Professor Devanathan, with some of the senior faculty at AC Tech, I may recall, a well-known professor of physics. And so PRS taught us classical mechanics and thermodynamics and so on. So he further developed my intense curiosity for physics, and particularly an appreciation for beautiful mathematical theories. And it was then around 72, 73, I decided that I was going to do a PhD and become a professor myself. And PR has played a very important role there. And that was followed by Professor Mohan. I hope he's in the audience. I'm very grateful to him. Professor Mohan was the instructor in the unit ops lab at the time, and he patiently tolerated my endless questioning of everything. And for that, I'm forever very grateful to him. And recalling other important professors, Professor Padmanabhan, who taught us electrical engineering. And from him, I learned the importance of conceptual elegance and logical inevitability. I mean, KP, as he was known, KP's lectures were absolutely delightful. They flowed effortlessly. One thing leading to the other, as I said, with a logical inevitability. And there was a sense of simplicity and elegance in his presentation that left a deep impression on me. And then we come to my dear friend and mentor, Dr. Sukumar Devota, who was also a PhD student at the time with KC. He taught me Fortran programming as an extra class after graduation, actually, as before I was just leaving for the US. And in that process, he introduced me to computing. Little did I realize that in 1977, I think this was sometime in April or May of 1977, when he conducted these classes for just the three of us. Little did I realize at the time that computing was going to become my career. And in fact, the last 40 years, most of my work has been in process systems engineering, using computing, particularly using artificial intelligence. And it all started with the lectures that Sukumar gave. And so, again, I'm very fortunate to have had him as a wonderful teacher and mentor in my career. And finally, of course, we come to Professor Casey, whom we are celebrating today. I met Casey only in my last year, or the last 2 years of my stay. It was a 5-year program in those days. I think I met him only in the 4th year, and then also in the 5th year. He taught us thermodynamics and played a very important role in shaping my career for a number of reasons. One of those was, just a little bit about the man himself. As this complicated tree on the left-hand side shows, that is the academic tree of a famous professor who taught at Imperial College London. His name was Roger Sargent. He is considered to be the Bhishmacharya of process systems engineering, with more than 1,000 descendants in the tree. And you see here on the right-hand side, in a smaller portion of the tree, Casey's name. Professor Chandrasekharan was the 3rd PhD student of Rogers. And Casey was also not only my thermodynamics teacher, he was also my bachelor's thesis advisor. Now, Casey also had several PhD students. 2 of those are, of course, Professor Mohan and Dr. Devota, shown here. Also shown there on the tree over here. And so in some sense, I'm related to this tree through Professor Casey and Mohan and Dr. Mohan and Dr. Devota. And some 10 years ago, I had the good fortune of meeting Professor Sargent himself. So there he is in the wheelchair. He was 92 or 93 at the time. I was invited by Imperial College to give the Roger Sargent lecture that year. This was in 2015, 9 years ago. And I spoke about AI in chemical engineering. You see the title there. And Roger sat through the entire lecture in the front row with his wife, who was also on a wheelchair next to him. And I had the great pleasure and honor of having Roger Sargent, who is sort of like an academic grandfather for me, attending my lecture and then joining me for the wonderful dinner, the banquet that the department had arranged. And it's interesting that Dr. Devorta and Dr. Mohan and Professor Casey, they all belong to that famous tree of Roger Sargent's. I myself belong to another tree as well. This belongs to the academic tree of Professor Keith Gubbins. These are the PhD students and postdocs shown there. And there in the photographs, you see Professor Gubbins, who actually happened to attend my Roger Sargent lecture in London in 2015. And this photo was taken at the time. I was his 12th PhD student, shown there in the red box. And interestingly, another person who is also associated with AC Tech very closely, and also with IIT Madras, and that is Professor Anand. He was also Professor Gubbins's PhD student, and he was his 6th PhD student. You see him in that red box. And Professor Anand is about 10 years senior to me. He graduated from AC Tech in 67. So there are all these interesting connections you see between AC Tech and other well-known institutions all over the world. And this is my own academic tree that one of my students prepared recently, a few years ago, which shows all the 42 PhD students I've had and master's students and postdocs. So it has been an exciting journey for me since leaving AC Tech. And roughly it's a 50-year odyssey, which I'm going to highlight. And it all started with my interest in physics and particularly thermodynamics as a first and second year student in AC Tech. So this all started, it goes back to 1972, 73, and to some extent 74 timeframe. So as you know, thermodynamics is the study of steam engines, and it is the science of predicting macroscopic behavior of trillions of molecules which don't have any purpose and given their individual properties. Now, Sadi Carnot is generally acknowledged as the father of thermodynamics. He wrote some of the earliest papers in this area in 1824, about 200 years ago. Lord Kelvin gave the name thermodynamics in 1854. Kelvin, as you know, is well known for this temperature scale and other major contributions to thermodynamics. The first law was conceived over roughly a couple of decades, the conservation of energy, due to the work of Mayer, Joule, and Clausius. These are all names in textbooks, you see. The second law of maximum entropy at equilibrium. Initially, entropy was discovered by Clausius. He gave the name entropy. Then came Gibbs and Boltzmann, who explained the true nature of entropy. And of course, Van der Waals equation was proposed in 1873. So I got really excited by thermodynamics, the ideas, powerful ideas of thermodynamics and how it can predict and explain all kinds of things. And also, particularly by Van der Waals equation, its simplicity, yet its power, left a huge impact on me. And so as a result, I became interested in thermodynamics as a first or second year student at AC Tech some 50 years ago. Now, thermodynamics tells you that things go from order to disorder. Whereas when you look around in the universe, look around in this planet, you see order everywhere, which seem to have come out of chaos or from disorder, right? Because we had Big Bang happen some 14 billion years ago, at which point everything was, all the elementary particles were in a disorderly state. From that total disorder, from chaos, how did we all come about? Roughly in 14 billion years or 13 billion years after the Big Bang, life originated on Earth from single cellular organisms. Over the last billion years or so, we all have evolved, and we are one of the most complicated as well as complex organized form of molecules where actually we are living intelligent beings. So how did that come about? Because thermodynamics seems to tell you, or the entropy principle seems to tell you, you go from order to disorder. But how did then life and consciousness originate? It is as if, like, you have a pile of wood there and you throw a bomb and then it explodes and out comes a house. And this would be unbelievable. If somebody demonstrates that, we wouldn't believe it. If somebody showed this as a movie, you would say that, oh, well, they are running the movie backwards. That is, it was initially a house, then the bomb went off, and then it went into a pile of rubble. But this is what seemed to have happened in the universe. Somehow, order out of chaos. And that seems to go against the second law. So I got interested in this question at AC Tech. I became interested in the question of life, origins of life, and origins of consciousness right there when I was a second year student. And it didn't make sense to me because the thermodynamics seems to suggest otherwise. So this became a lifelong passion and a lifelong pursuit for me. And there are more examples of this. You see self-organizing dynamics and emergent order everywhere. On the left-hand side, you see the bacterial chemotaxis, where if I were to run these videos, you can find these videos on YouTube. You'll find bacteria self-organize and chase after food. There is a sugar crystal that shows there in the black. The second one is an ant crater formation where ants transport sand out from the hole under the ground in order to create a nest. And there is an orderly structure that emerges. And then the flight of starlings, where the birds, form flocks to escape predators and so on. So the question I became interested in AC Tech, and then pursued it further in my grad school at Cornell, was that could there be unifying organizing principles behind such collective behavior? It seems unlikely, right? Because they're all different species, different scales, different phenomena. Why should there be a common principle? But then in nature, generally, nature only uses a handful of tricks in her design. She doesn't do, millions of things to create, millions of things. In physics, for example, the trick she uses is symmetry. All the fundamental laws of physics can be derived from the symmetry principles of the Lagrangian, or the symmetry properties of the Lagrangian. So the key insight from physics for me was, if you want to get to the bottom of things, look for invariants, things that don't change. Okay. So now, if you look at the 20th century science, it was largely reductionist in character. We went from macroscopic matter to molecules and atoms and protons and neutrons and quarks, maybe strings. So we went down and down and down. And in that process, we were spectacularly successful. We discovered quantum mechanics, elementary particle physics. Even biology was very successful going down this route with double helix and whatnot. By my estimate, some 600 Nobel Prizes have been awarded in the last 120 years for pursuing the reductionist paradigm. But can reductionism answer the following question? That is, if I give you the properties of an individual neuron, which we know very well in many cases, and then I tell you I'm going to organize 100 billion of them in a particular way, can you predict the behavior of the system? That is, can you go from neuron to brain to mind? For example, an individual neuron is not conscious, but the 100 billion of them in a brain together is conscious, self-aware. How does that come about? So how do you go from parts to system? This cannot be solved by reductionism because there is nothing left to reduce. Now you are actually going in the opposite direction. You are putting things together. So you need a constructionist or emergentist approach. And this is what I've been pursuing for the last 40 years or so. Now, so we want to go from individual agent properties to emergent properties of millions of agents. We know how to do this. This is what thermodynamics is about. In particular, this is what statistical thermodynamics is all about. If I give you the properties of molecules, I can predict the properties of a gas. But my question is, can we do this for goal-driven systems, such as neurons and bacteria and birds and people? That is, can we generalize statistical thermodynamics for these kind of agents? And that's what I ended up working on for the last 40 years. And then in that process, I created this new framework, which I call statistical teleodynamics. Telos means goal in Greek. In thermodynamics, the molecules, the agents switch states driven by thermal agitation. In teleodynamics, the agents switch states driven by their pursuit of goals. And so hence the name teleodynamics. And just like, so teleodynamics can be thought of as statistical thermodynamics plus game theory. Okay, so what is game theory? Very quickly, as you know, probability theory came out of experiments with games of chance, like gambling. Bernoulli and Laplace and others developed probability theory by, observing how games of chance, like card playing and so on, take out throwing a dice. Similarly, games of strategy gave birth to game theory, and developed by von Neumann and Morgenstern and so on. And in game theory, the goal is you are given a set of strategically interacting players. Each player executes the best possible strategy that maximizes that player's utility. The goal is to predict what strategies will be executed and what outcomes are likely. And in particular, will there be an equilibrium outcome? Now, John Nash, shown here on the left-hand side in the black and white photograph, was a famous mathematician at Princeton, and who published a very important paper on non-cooperative games and proved that these games will reach an equilibrium called Nash equilibrium. And on the right-hand side, the photograph, you see the movie made out of his life called A Beautiful Mind. I don't know whether you've seen it. If you haven't, it's worth a look. Russell Crowe there plays John Nash. And this was Nash's paper I show there. It's appeared in the Proceedings of the National Academy of Sciences in the US. Even though it is on 2 pages, it's really a one-page proof. It's a one-page paper which starts at the bottom, you see here, and ends over here. So it's really about 1 page long. For this 1-page contribution, Nash got his PhD in mathematics at Princeton. Not only that, for this 1-page contribution, he won the Nobel Prize in economics in 1994. So I tell my students that we can all accomplish a lot just in 1 page. See Nash as a role model. And so when you take game theory and combine it with statistical thermodynamics, you get statistical teleodynamics. And it is the framework for analyzing situations such as how people search for jobs in an economic free market. For example, people in a job fair shown here, they're looking for jobs which would pay them higher salary, for example, or better quality of work, better title, more perks, and so on. And this is just like people switching lanes in a busy road. When you see, this is rush hour traffic in Los Angeles, and every lane is clogged, so things are all moving slowly. You want to get home quickly, and but you stay in the same lane because every other lane seems to be moving at the same speed. But suppose a new lane opens up, and you suddenly see an opportunity, you switch. But then the same idea occurs to others, and they also switch, and pretty soon that lane also gets crowded and slow. And so then at that point, people stop switching. And this is called an arbitrage equilibrium, because there are arbitrage opportunities are gone when everybody seizes them. And so all lanes have the same time to travel, T1, T2, T3, they're all the same. So this idea of arbitrage equilibrium is what I applied to other, which comes out of economics and game theory to other systems in biology and so on. And so in statistical teleodynamics, there are three laws, just like the three or four laws of thermodynamics, depending on which ones you're talking about. But generally, people talk about the two laws of thermodynamics, and similarly, there are two laws of teleodynamics. But there is the zeroth law, which says goal-driven agents constantly pursue higher utility to survive. So this is a given. That's why it's the zeroth law. Then the first law says the environment imposes constraints on survival performance. And this is equivalent to the first law of thermodynamics. And the second law is the self-organized competition results in arbitrage equilibrium. And this is equivalent to the maximum entropy principle in thermodynamics. And using potential game, I was able to show that the income distribution in a free market will follow a log normal distribution, as shown here in salary. And then that's how it looks like. And at equilibrium, everybody will enjoy the same utility. And I'm going to skip all the mathematics in the interest of time. And so here we went from agent level property to the system level property. I ended up writing a book about it. And so we can see how this theory works in practice. We can compare the theoretical predictions with actual income data we have for certain countries, for the top 1% of the population, the bottom 90%, and the middle 10 to 1. And I define a non-ideal inequality coefficient psi, which is 0 if there is fair inequality, because the actual share will be the same as ideal share, and so psi will be 0, and it won't be 0 if the inequality is unfair. Okay, so let's see what the data looks like for Norway. So this is about 100 years of pre-tax labor income data that is available for Norway. And you see the bottom 90%, if it were ideally enjoying its reward, then psi should be 0 and it will be along the x-axis. But you see that it is not. It is below the x-axis. That means the bottom 90% is getting less than its fair share. But in the last 25 years, it has come close to the ideal value, so it's not too bad. And particularly, this is pre-tax. Once you apply progressive taxation on this curve actually shifts up. And so the bottom 90% is doing quite well in Norway. This is the middle 10 to 1. And you can see that that is also hugging the x-axis very closely. And the top 1% do very well no matter where you go. They make more than their fair share according to this model. And so the theory seems to get the bottom 99% right. And if you look at the US for the same kind of data, you see that the bottom 90% has steadily lost ground, whereas in Norway, the bottom 90% improved in the last 25 years. Here in the US, people have suffered, and that explains some of the dysfunctional politics that we're all having now. But even in the US, things were much better for about 30 years after the Second World War, from 1945 to 1975. And the other countries in Europe are somewhere in between. Norway, Sweden, Denmark are the fairest inequality, and the bottom at the other extreme is the US. Okay, so now economic inequality belongs to a broad class of problems. This sort of self-organizing emergent phenomena show up in all kinds of places, in biology, ecology, sociology, and economics. Economics is what I talked about, and the other things, there are many examples of this. As I showed before, the birds flocking or the ant craters and so on. So in passive matter, when forces are equal, you have mechanical equilibrium. When temperatures are equal, we call it thermal equilibrium. When chemical potentials are equal, you have phase equilibrium. In active matter, similarly, when the effective utilities are equal, you have arbitrage equilibrium, which is what all these systems are in. And so this is a very quick overview of what I've done in the last 50 years, where my interest in thermodynamics started in AC Tech, roughly around 74, maybe 73, through the lectures of PRS and Casey and others. And particularly got interested in van der Waals equation and those ideas of going from fundamental properties to deriving macroscopic properties. And so that led me to teleodynamics some 50 years later. And this is what I'm excited about. This is what I'm working on these days. And would like to end with this well-known குறள் from Thiruvallur. எப்பொருள் யார் யார் வாய் கேட்பினும் அப்பொருள் மெய்ப்பொருள் காண்பதறிவு. So in this, if you know Tamil, you'll understand the meaning. Thiruvallur really defines what is research. So because don't just take it for granted because someone said so. Dig into it and try to understand it. And that is essentially what research is all about. And this has been a guiding um, uh, principle for me, which comes from Thiruvallur some 2,000 years ago. Once again, thank you very much for giving me this opportunity to share my work with you, and thank you for listening. Once again, I'm very grateful to Dr. Devota and his colleagues at ACTech for organizing this event and for inviting me. And once again, I'm very grateful to all the wonderful teachers I've had at ACTech. As I mentioned, Professor P.R. Subramaniam, Professor K. Padmanabhan, Dr. Mohan, Dr. Devota, and of course, Professor K. Chandrasekharan. And I hope all of you have a wonderful celebration and enjoy the festivities. Thank you very much. Bye.